In this lecture, we're going to see about the infinite square well. So we're going to solve our first quantum mechanical problem. Okay, we're going to solve our first quantum mechanical problem, and the problem we'll solve is the infinite square well. So here, a particle is trapped in a potential well. So this potential well is not kind of a physical well, but what it means here is on the boundaries between the region 0 to A, the potential is 0. Okay, the potential is 0. Here you have the conditions. And at the boundaries, the potential is infinity. So a particle trapped between the region 0 to A should acquire how much ever energy it acquires, it won't be able to escape this potential well, because here the energy at the boundaries is infinity. So if it acquires 100, 1000, 2000, how much ever energy it acquires, it will not be able to escape this well. So the energy of the particle is E. So we'll write it all down. Now we'll solve the Schrodinger equation. So first step to solving the so first let's write out the Schrodinger equation. So the Schrodinger equation is minus h square 2m, right? And we have dx square plus b, right? Plus b, and all this is the operator, and it is operated on the function psi, right? On the function psi is equal to e psi. Now we are going to take first the region inside. Okay, the region inside. So the inside the region, so then inside the region 0 to A, the potential is 0. So the Schrodinger equation reduces to this expression here. And then we can rewrite the Schrodinger equation in this way, where K is defined to be this quantity. So once you define it like this is nothing but the simple harmonic oscillator problem, right? Here acceleration, and here you have the some constant square, and here you have the function again, right? Displacement. So it's like, so the solution will be like a simple harmonic oscillator solution. So the solution is written out in equation 2.18. So now all problems will be using something called the boundary conditions. So what the boundary condition says is, so if phi is some function like, it's going like this here, the after at the boundary, now phi should be continuous at the boundary. So at x is equal to 0, x is equal to 0, and at x is equal to a, the phi should be continuous. Okay, phi should be continuous. It can't it is called the continuity condition. Okay, so and at these boundaries it should go to 0. At these boundaries the probability amplitude should go to 0. Now when we apply that condition to this solution that we got here, we substitute phi is equal to 0, and then we substitute phi is equal to a and set it equal to 0. We'll see that what can we tell about the terms that we get. We see that, so the condition sets that b should be equal to 0, because when phi is equal to 0, you get an answer b, but we know that phi naught should be, phi of 0 should be 0, so we have to set b equal to 0. So the only remaining term would be sine kx. Okay, a sine kx. Now we have to find the value of k. So to find the value of k, we substitute in phi the for a, we substitute in the place of x, we substitute a, and set that equal to 0. We have to find the argument. Okay, we have to find the argument for ka sine ka such that it goes to 0. So what values of k will make this term sine go to 0? So the values are given here: 0, plus or minus pi, plus or minus 2 pi. So you can see that sine will go to 0 in 2 pi plus and pi and 3 pi, like that. So that's why we set it k is equal to these values. Now, so this can generally be written as k. So this, for this set of terms, the general equation for kn can then be, k can be written as n pi by a. where n is going from integers 1, 2 and 3. Okay, so now we have a, so now what we can say is, because of this introduction of n, the solution is actually quantized, right? The we'll come to it. We'll say that the energy itself is quantized. Here, how we obtain that is, now k itself is given by k and E are related by this relation. So you substitute the value of k here into this equation, where we have defined k to be in terms of energy, and you will get this expression. Now when we substitute it here, the value of k, kn, u, we substitute it here, you will get this expression for En. So because of this presence of this term n, which is has values 1, 2, 3, we say that the energy is actually quantized. So this is what is called quantization, right? So it cannot take all continuous values, but it has to take discrete values, which is quantized by the number n. Now next we have, what we have to do is, we have the solution. Now we have obtained the solution, but we have to normalize the solution, because this phi is actually interpreted, this phi that we obtained here, this phi that we got here, is actually interpreted to be the probability density function, right? So phi square, so phi can actually have values, so sine has actually a negative value, so we don't take negative. Probability doesn't have any meaning, so normally we take psi square, probability amplitude, right? Probability amplitude. So when we take sine square, now this has to be normalized to 1, such that now you take the square of this function and set it equal to 1, okay, and find what the value of a should be. So the value of a is found, the constant is found using the normalization condition. It is found to be square root of 2 by a. Okay, so we substitute that, and we substitute k, value of k here, and we have obtained the solution for a infinite square well, right? Infinite square well.